Tonight, right before you go to sleep, you are highly likely to do something that, well, defies pretty much all of human biology.
Yeah, almost definitely.
You're going to pull this, like, concentrated slice of the midday sun right out of your pocket, hold it maybe 12 inches from your face, and just shine it directly into your eyes.
And your brain is going to react exactly as if you were standing outside at high noon. It's wild.
It really is. So, welcome to this personalized deep dive. We've got a really fascinating stack of source material today, specifically a comprehensive text titled LCD LED Screen Light Effects and Optimization.
It's a great read. Really eye-opening. Pun intended, I guess.
Right. And our mission here isn't just to tell you that screens are bad. I mean, we all get enough of that guilt trip, you know.
Absolutely. We don't need another lecture on screen time.
Exactly. So what we're going to do is extract the exact underlying physiological mechanisms of how that light actually interacts with your body. And more importantly, we want to walk away with scientifically backed strategies to optimize your tech habits.
Because, let's face it, none of us are throwing our devices into the ocean anytime soon. We have to live with them.
Right. We need our jobs. Okay, let's unpack this. What's the best place to start?
Well, the most crucial starting point from the text is actually correcting a really widespread assumption about the hardware itself. Like, we constantly hear the term LCD screen.
We got an LCD TV, LCD monitor. It's everywhere.
Exactly. But it gives us a fundamentally skewed idea of what kind of light we're actually being exposed to.
Right, because I was reading through the source text and realized my entire mental model of how my television works was just completely wrong. Like, LCD light is basically a misnomer, isn't it? The liquid crystals don't emit anything at all.
They don't. I mean, LCD stands for liquid crystal display, sure, but those crystals are just acting like millions of microscopic shutters.
Oh, like window blinds.
Yeah, exactly like blinds. They twist and untwist to block light or let it pass through so you can see shapes and colors. But the actual light source, the backlight sitting behind those shutters, is what really matters.
And what is that backlight made of?
Well, in virtually all modern devices, that backlight is entirely LED-based.
Okay, so whether you're, looking at an email on your phone or a massive spreadsheet on your work monitor or watching a movie on a flat-screen TV, you're essentially looking into an LED flashlight.
That is the biological reality, yes. And the issue is that LED backlights do not produce a balanced full-spectrum light like natural sunlight does.
Right, they're engineered differently.
Very differently. They are highly engineered to be extremely bright and energy efficient. And to achieve that, they emit a massive proportion of short-wavelength light.
Which means what exactly for our eyes?
We're talking specifically about a heavy, heavy spike in the blue light range, right around 450 to 495 nanometers on the visible light spectrum.
Okay, so wait, I read this part and it blew my mind. So our eyes actually have this secondary, completely hidden security system that doesn't even process vision. Like, it's just there looking for the color blue.
Yes. It's incredible. The text identifies a specific class of cells in our retinas, and they're called intrinsically photosensitive retinal ganglion cells.
That is a mouthful.
It is. We just call them IPRGCs for short. So, your standard rods and cones are busy doing the actual work of vision, right?
Like detecting the shape of a dog or the color of a car.
Right, or the movement of a ball. But the IPRGCs are doing something entirely separate. They act as ambient light meters.
Oh, wow. So they're just measuring the room.
Exactly. And they have a direct non-visual neural pathway that goes straight to the hypothalamus in the brain.
And hypothalamus is basically the master command center for the body's internal clock, right?
It is. It houses the circadian regulation center. So it dictates the whole ebb and flow of our daily hormones. When we feel alert, when our digestion peaks, and crucially, when we feel sleepy.
And that whole mechanism relies on light.
Almost entirely on light. So when those IPRGCs in your eye detect that specific 450 to 495 nanometer blue light we talked about, they fire off a signal to the hypothalamus.
And what does the signal say?
It essentially says, hey, the sky is bright blue, it is daytime, keep the engine running. And the immediate physiological result of that is the total suppression of melatonin production.
Which is the exact hormone we absolutely need to initiate and maintain quality sleep.
Right. Without melatonin rising naturally in the evening, your entire circadian phase gets delayed.
So you just lie there staring at the ceiling.
Yeah, it takes you significantly longer to fall asleep. And even when you do, the structural quality of that sleep degrades. Over time, you just build up this chronic accumulation of daytime fatigue.
Okay, I mean, I hear the midday sun analogy, but come on, I'm looking at a 6-inch phone screen, right? I'm not staring directly up at the actual sun in the sky.
Sure, yeah.
So how can something so small genuinely override millions of years of evolution? Like, is it really that powerful, or are we just fear-mongering a little bit here?
No, it's a completely fair question. It really comes down to proximity and concentration. I mean, the sun is vastly brighter, yes, but it's also 93 million miles away.
Right. And you rarely stare directly into it, hopefully.
Hopefully, but your phone is literally inches from your face. The light is being channeled directly into the retina, bypassing a lot of natural environmental diffusion that you'd get outdoors.
Oh, that makes sense. It's like a laser pointer versus a floodlight.
Exactly. Furthermore, the peak emission of that LED perfectly overlaps with the exact sensitivity peak of those iPRGC cells.
Oh, wow. So it's perfectly tuned to trigger them.
Perfectly tuned. So it's not about the total volume of light in the room. It's about a highly specific, concentrated signal hitting a highly sensitive biological trigger.
Okay, well, if it's that powerful of a signal, my mind immediately goes to the worst case scenarios. I mean, if you hear concentrated energy hitting the retina, you start worrying you're like microwaving your brain or burning out your eyes.
Yeah, and we definitely need to firmly separate the mechanisms from the myths here. The source material is very clear on what is absolutely not supported by evidence.
Okay, good. Let's clear the air.
First, there is no credible evidence whatsoever that your daily screens emit harmful ionizing radiation. You are not getting X-rayed by your tablet.
Good to know. I can take my tinfoil hat off.
Please do. Additionally, there's no evidence of permanent structural eye damage from normal screen use. You are not burning a physical hole in your macula.
Okay.
And there is no such thing as toxic light in a chemical or poisoning sense. The light itself isn't a toxin.
Okay, so if the hardware isn't physically destroying my eyeball, the actual danger is just purely about timing. We are essentially giving ourselves severe jet lag without ever crossing a time zone.
That is exactly it. The scientific concept outlined in the text is temporal misalignment. Human biology fundamentally expects environmental light contrast to encode time.
Meaning bright light is day, dim light is night.
Right. Bright blue rich light means day, and dim warm light like a campfire or the setting sun means night. Screens just absolutely shatter this biological expectation.
To confuse the system.
Profoundly. They introduce profound circadian confusion. Your brain no longer has clear environmental boundaries between waking hours and resting hours.
And it goes deeper than just the light spectrum, doesn't it? Because, like, if you're listening to this right now, you might be scrolling through a news feed or answering a really stressful email. The text highlights that the light is delivering a psychological payload alongside the photons.
Oh, yeah. The cognitive load is a massive factor. It's a physiological double punch.
A double punch. Okay, break that down.
Well, you have the high brightness blue light suppressing your melatonin, keeping the biological clock stuck in the daytime. But simultaneously, you have this rapid information delivery.
Right. The notifications, the infinite scrolling feeds.
Exactly. High-stakes emails, social media, it's all designed into continuous engagement loops.
So your nervous system is basically locked into threat assessment or reward-seeking mode.
Which severely delays your body's ability to transition into the parasympathetic state, commonly known as rest and digest.
So even if you fix the light, the content is still keeping you awake.
Yeah. Even if you were wearing, like, perfect blue-blocking glasses, engaging with highly stimulating content keeps your brain flooded with cortisol and adrenaline.
Yeah.
You become physically awake from the light spectrum and psychologically wired from the interface.
Wow. Okay, so the sleep architecture is totally ruined.
Yeah.
But what about the waking hours? Because I'm sitting here realizing that by like 4 in the afternoon, my eyes often feel like they're filled with sand.
Oh, I know the feeling.
Even if there's no permanent structural damage, the physical discomfort is really intense. What's happening there?
So the text details the realities of digital eye strain. And remember, this is functional strain, not structural damage. Screens create highly unnatural visual conditions. Think about reading a printed book, for example.
Okay, the light is reflected off the page.
Right, the light is reflected, the contrast is softer, and the text has a natural texture. But a screen is a backlit, high-contrast environment with a fixed focal distance.
Right, let's break down that fixed focal distance, because our eyes have these tiny little muscles,
Yeah.
the ciliary muscles, right?
Yes, exactly.
Think of them like the internal gears trying to focus a complex camera lens. When you look at a mountain way out in the distance, they relax. When you look at your thumb right in front of you, they contract.
Perfect analogy.
So when you stare at a monitor exactly, say, 22 inches from your face for 4 straight hours, those little gears get locked into a single high-tension position. And eventually, they just start to cramp up.
That sustained muscle contraction is a primary driver of those tension headaches people get right behind their eyes. But honestly, the most jarring statistic from the source material regarding physical strain is the impact on our blink rate.
Oh, right. I was shocked by this.
When we engage with the digital screen, our blink rate decreases by roughly 50%.
Wait, half? I'm just sitting there completely wide-eyed, not blinking for minutes at a time.
Essentially, yes, you are in a staring contest with a piece of glass, and the glass is winning.
That's horrifying. Why does that happen?
The cognitive engagement with the changing pixels is so high that the automatic autonomic blink reflex is just suppressed.
And I'm guessing the symptoms of a half blink rate are pretty immediate.
Very immediate. The tear film on the surface of the eye evaporates much faster than it can be replaced. This leads to severe dryness, that gritty feeling you mentioned, blurring of your vision, and a really deep aching fatigue.
It's terrifying how quickly a normal behavior becomes physically punishing.
Hmm.
And the text introduces another variable causing this strain, one that I had absolutely no idea about, and I consider myself pretty tech savvy.
You're talking about pulse width modulation, right? PWM.
Yes, PWM. What is this?
What's fascinating here is the engineering workaround manufacturers use to control screen brightness. So think about a traditional incandescent light bulb. It dims smoothly, right?
Yeah, you turn the dial, it just gets softer.
Right. You reduce the voltage, the filament cools down, and the light gets softer. LEDs don't function that way. To maintain their color accuracy, they generally need to run at full power all the time.
Wait, so how do they dim then?
So to make an LED screen look dimmer, engineers use pulse width modulation.
Meaning they don't actually dim the light at all. They just turn the backlight completely off and then back on again, incredibly fast.
Exactly, they flicker it. If you set your phone brightness to 50%, the LED isn't running at half power. It is blasting at 100% brightness, but it's turning itself completely off for 50% of the time.
That's insane.
It's cycling so rapidly that your conscious brain averages the light output and perceives it as a steady, dimmer image.
So I thought I was being smart by turning my brightness down in a dark room. But in reality, I've just turned my phone into a high-speed strobe light.
That's a great way to put it. It is producing rapid micro-flickering. And this is where the biology gets complicated. While this flickering is consciously invisible to you, your optic nerve and your visual cortex are absolutely still detecting and processing those rapid, high-contrast flashes of light and darkness.
That sounds completely exhausting for the nervous system.
It is. Now, the neurological toll is highly individual. Some people are entirely unaffected. But for a significant portion of the population, this micro-flickering causes profound eye fatigue, sudden tension headaches, and a general sense of neurological discomfort.
Like getting nauseous from looking at a screen.
Exactly. A person might feel nauseous or strained after looking at their tablet for just 10 minutes and have absolutely no idea why. They might assume it's the content when it's actually the invisible flicker rate of the hardware.
So I'm sitting here realizing my entire daily routine is a biological disaster. I've got, blue light tricking my hypothalamus. I'm blinking half as much as I should. My eye muscles are cramped, and my screen is micro-flickering directly into my optic nerve.
It paints a grim picture, for sure.
But I can't throw my laptop in the ocean because I need my job. So how do I actually survive this? What is the optimization playbook from the source text?
Well, the incredibly good news here is that because we are dealing with functional strain and temporal signals, behavioral and environmental tweaks are highly effective.
Good. Give me the first one.
The very first strategy is spectrum control. If short wavelength blue light suppresses melatonin and signals daytime, we need to aggressively remove that wavelength as the actual sun goes down.
This is where the software solutions come in, right? The text mentions tools like Night Shift on iOS devices, Nightlight on Windows, or third-party applications like f.lux.
Yes, those are perfect. These programs actually calculate your local sunset based on your time zone. As evening approaches, they automatically shift the color temperature of your display.
Making it look warmer.
Right.
Yeah.
They pull out the blues and greens and push the entire screen toward warmer red and orange hues. By doing this, they strip out that peak wavelength that triggers the iPRGC cells, drastically reducing the melatonin suppressing effect.
It does look pretty strange at first, I have to say. Like your pristine screen suddenly turns a murky pumpkin color.
It really does.
But it's amazing how fast your brain color corrects. After about 5 minutes, you don't even notice it. But just turning the screen orange isn't enough to solve the whole problem, right? We still have to deal with the sheer intensity of the light.
Exactly. And this brings us to brightness alignment, which is a vital rule in the text. Your screen brightness should ideally be less than or equal to your ambient room brightness.
Less than or equal to the room. So my habit of lying in a pitch-black bedroom, staring at a glowing white screen, is a massive red flag.
It's one of the worst things you can do. It creates immense high contrast stress on the visual system. Think about it. Your pupils dilate because the room is dark, letting in more light, but then you are staring at a bright focal point.
It's the biological equivalent of staring directly into a flashlight in a dark cave.
Precisely. At night, you need to aggressively reduce the brightness of your device, but equally importantly, you must manage your environmental lighting. The text strongly recommends maintaining low-level, warm ambient light in the room.
So instead of a totally dark room, maybe you have a small lamp on in the corner.
Yes, and preferably equipped with a warm spectrum, bulb yellows, oranges, or reds. Indirect sources are heavily preferred too.
What do you mean by indirect?
Like, bounce the light off a wall or a ceiling rather than having the bare bulb shine directly into your visual field. This reduces the contrast ratio between your screen and your environment, allowing your eyes to relax.
Okay, so we've got the spectrum warmed up to a nice pumpkin hue, we've matched the brightness to the room, and we've turned on a warm lamp in the corner. What about the physical strain of staring? You know, the staring contest we're constantly losing.
For visual behavior, the text advocates for the 20-20-20 principle.
Oh, I've heard of this. Every 20 minutes, look at an object 20 feet away for 20 seconds.
That's the one. It is a simple but profound mechanical reset. By looking 20 feet away, you force those ciliary muscles, the internal gears, to disengage from their fixed high-tension state and recalibrate.
And what about the blinking?
Combine that physical break with a conscious, deliberate effort to blink rapidly several times. That redistributes the tear film, and you can significantly mitigate digital eye strain.
But wait, this brings up a massive paradox with the invisible flicker we talked about earlier.
Ah, the PWM issue.
Right. If I'm supposed to turn my screen brightness down at night to match my dimly lit room, won't that make the PWM microflickering worse? Because the LED has to spend more time in the off state to simulate that dimness.
Yes. This raises a very complex problem for user optimization. If you know your specific device uses low-frequency PWM, and you can often find this buried in the technical specifications or through third-party hardware reviews, dropping the brightness to minimum levels will dramatically exacerbate the microflicker.
So it's a catch-22.
In these specific cases, yeah, you might be trading a circadian issue for a neurological one. You avoid suppressing your melatonin, but you give yourself a piercing tension headache.
So what's the workaround? Which evil do I choose?
Well, the long-term structural solution is to look for monitors and devices that advertise DC dimming or boast extremely high PWM frequencies.
What does DC dimming do?
DC dimming actually reduces the electrical current to the LED to dim it, avoiding the flicker entirely.
Oh, perfect.
But in the short term, with the devices you currently own, if you are highly sensitive to flicker, you may need to keep your screen brightness slightly higher to reduce the strobe effect.
But then how do you protect your sleep?
To compensate, you must rely much more heavily on blue light blocking software, perhaps even wear physical blue blocking glasses and maintain brighter, warm, ambient room light to offset the screen's intensity.
It really requires playing detective with your own biology to find that specific sweet spot. But looking at the source material, there's an elephant in the room. The text refers to this as the single most impactful variable of all, temporal boundaries.
Yeah, this is the hard truth.
Yeah.
We can optimize the spectrum, we can perfectly align the brightness, we can blink constantly, and we can eliminate the flicker. But even a perfectly optimized, warm, dim screen is going to disrupt your sleep architecture if you engage with it for prolonged periods directly before attempting to sleep.
The sheer duration of exposure matters.
Absolutely.
Because even warm, dim light is still light hitting the retina. And to our deep evolutionary brain, light of any kind still signifies wakefulness. Not to mention the psychological payload of the content keeping the nervous system engaged.
Exactly. The ultimate non-negotiable recommendation from the source material is behavioral. You must reduce or completely eliminate screen exposure 1 to 2 hours before your target sleep time.
So put the phone down at 9 p.m. if you want to sleep at 10:30.
Right. You have to give your nervous system a buffer zone to transition out of that alert threat assessment state. The biology simply requires time for melatonin levels to rise naturally in a dimly lit environment.
So what does this all mean? If we pull all the way back and look at the system-level summary of our deep dive today. The core issue isn't the laptop or the phone itself. We aren't being poisoned by toxic rays. The core biological friction is temporal misalignment.
That's the perfect summary.
We're walking around with a biology that fundamentally expects the physical environment to encode time-bright, blue, and high contrast for the daytime, dim, warm, and low contrast for the night. And we've surrounded ourselves with technology that blasts contradictory signals into our retinas, completely confusing our deepest internal clocks.
It's a massive biological mix-up.
So sustaining our health, then, isn't about retreating to a cave and throwing our technology away. It is about actively and consciously restoring coherent light timing in our daily routines.
And if we connect these mechanisms to the broader human picture, it leads to a rather profound realization.
Oh, what's that?
Well, human biology fundamentally relies on environmental light to encode the passage of time. For the entirety of human history, our species shared one master synchronized clock, the physical rotation of the Earth and the rising and setting of the sun.
Right. We were all on the same schedule, essentially.
Yeah. But today, we are completely controlling our microenvironments with artificial screens, which leaves us with a lingering thought. Are we effectively creating our own isolated biological time zones?
Oh, wow.
And if every single person is walking around in their own custom-lit time zone, experiencing biological noon at midnight, what happens to the shared human experience when our internal clocks become entirely disconnected from the natural rhythms of the planet we live on?
That is a wild, slightly existential thought to end on, from optimizing a laptop setting to questioning our connection to the rotation of the Earth itself. Well, thank you so much for joining us on this deep dive. Hopefully you can take some of these specific insights, the warm ambient light, the 20-20-20 rule, the awareness of the invisible signals your screen is sending to your hypothalamus, and bring them into your evening routine tonight. Try creating that clear physical boundary between day and night and see how your body responds. Until next time.